Let's see. Okay. Uh, I I don't. Um, you guys have any questions, anything? Because we got a couple of minutes in the
Wondering on the homework,
or,
part A. This may just be an edit. You talked about figure 4H. I think it might be referencing figure 2H of that paper. It's 4H.
oh yeah. I think you're right. Yeah, it should have been 2H.
Okay.
Yeah, I don't know why I said 4H.
It's really the only H diagram in there.
Oh, there is a figure 4, yeah, but no H.
Yeah.
Yeah, that's kind of like the main part of the quiz, I think, or homework, but thanks. Yeah, I totally missed that. Hmm. Maybe it was subconscious, like 4H is like an organization, I guess, you know. That would have been a yeah, subconscious thing. It's supposed to be 2H.
The homework it talks about figure 4H.
Yeah.
2H.
It's like that thing. Right, yeah. Good point.
It's looking in the wrong place.
Yeah. Right. Um, So why don't I just get started? As people show up later, but so yeah, the homework's going to be is just like a eutectic like this. Like eutectic is kind of a main question. I went through how to just kind of what a eutectic is, and you can get it from the thermocalc or from the CalFAD programs. And then the eutectic is going to have these weird structures because you have this separation into two crystalline phases from liquid, and it's kind of a race to see which one you can form. So there's a competition between the thermodynamics of separating out and the kinetics of moving the atoms. And that ends up giving you these kind of almost like diffusion fronts, right, that give you some kind of tiger skin looking morphology. So you can always tell that you have a eutectic, and then a lot of the game is like figuring out if you have a micrograph of something, like where did it, like where did that come from? It's like it's kind of reverse engineering from a micrograph to figure out where it came from in the phase diagram. So there's a couple questions like that in the homework thing. Anyway, so they in the previous in the solutions chapter, so we looked at this kind of phase diagram. So you cool it down, it phase separates into two phases, right? So you have this little liquid phase separation. So you have two liquid phases. Right? So you quench down, then it goes to a binodal phases. So if you quench into the binodal region, which is between the spinodal and the binodal line, then you get kind of droplets form. If you quench into the spinodal region between the spinodal lines, then you can get this kind of web structure that somehow looks pretty reminiscent of this thing, of the eutectic structure. And kind of the same reason in a sense. I mean, it's basically a competition. So Kahn-Hilliard theory describes the kinetics of separating in the spinodal region. It's basically a balance between the transport and the thermodynamics that leads to some kind of web-like structure. So that's this phase diagram can be constructed directly just from a simple like Hildebrandt equation, right? So the question is like, how do you get something like that, like a eutectic phase diagram, right? I mean, now would you have this simple model mixing that's got this kind of a marble equation with the log terms and composition, then you add in an enthalpy term. And then, and then if you plot that out, you get these kind of U-shaped free energy of mixing curves for the miscible region. And if you get into this immiscible region, you get a double hump, and the double humps give you the binodal points in the two-phase region. So in a single phase region, it's just this U-shaped thing. It doesn't look like a U-shaped thing could give you that phase diagram. Like doesn't seem to be any connection, right? Yeah, it's possible. So the book, this is pretty much from the book, right? So it's nice to see. So each of these curves would be like a miscible phase curve, like one of these curves, right? Except that you have two phases. So this is liquid, so it's kind of the same phase. And this is two phases, like a solution, a solid and a liquid phase. Right? So you're trying to generate this phase diagram. We have a solid solution. So you have, not sure if they say, but they get that with silicon and germanium. It's going to generate a phase diagram like that. Right? So basically, you can get that if you have a separate liquid and a separate solid curves, and then you have the parameters in this. In other words, the chi parameter or the Margulis or the Hildebrandt interaction parameter that for the two components, it differs so that it generates these two curves. So we'll talk about like what values you need to have for the Hildebrand solubility parameter in order to get this to happen, right? So in fact, by playing around with those parameters, you can get a lot of different phase behavior. Like in other words, you have two A12 terms, like Margulis terms. So by those can be positive or negative, and then you can change the shape of these curves and get basically any phase behavior you want by doing that. Okay, so but anyway, to get this, so if you're at here, there's a plot of this whole thing. So if you're at like T1, you're in the miscible regime, it's liquid. So the liquid curve is below the solid curve. So basically you just have liquid and it's miscible across the entire composition range. Right, so if you take any point here, point 2, if you fluctuate the composition, it's steeper up than down, so it'll always spring back because you're increasing the free energy by a fluctuation. So it wants to go back to what you put in for any point on that curve, especially for the critical composition, right, where it's always uphill. And then, so if you go to T2, so as you go T1, T2, so this Margulis coefficient is going to be inverse temperature, right? It's going to be like enthalpy of interaction divided by T. So as you change the temperature, the value of that thing changes, but it's going to change differently for the solid and the liquid. So as you reach a point T2, then at the corner, the two free energies are equal, right? So that's the miscibility limit where you start to form a crystal in the dilute germanium, so pure silicon. That's like the melting point of silicon, that's the melting point of germanium in the side by side. They're both diamond cubic crystal structures. So anyway, so you go to T2 and you get that point, and if you go to T3, then you have the two phases in equilibrium. So that means that the solid and liquid curves cross, and you can draw a common tangent, and that common tangent defines the two phases that are in equilibrium with each other, a solid and a liquid phase. And if you go below in composition, then you're on this side of that phase equilibria, and then you have the same situation before. Any fluctuation in composition there, steeper uphill than downhill, so it springs back because you want to lower the free energy overall. So the combined free energies are lower for the mixture than they are for the separating out fluctuations. Right, and then if you're in this region, you separate to those two phases that have the same chemical potential because the slope of the free energy versus composition is a chemical potential. So those two phases are in equilibrium with each other. So if you're in between the two phases, you're in this region, right? And if you go to T4, same thing happens, but it shifts over to the right. So the compositions shift to the right. So you have a common tangent here. Two phases have shifted to the right. And finally, you get to the point where you're at the liquid phase totally disappears. And you're at this melting point for germanium. Right. So just by having two of this type free energies for the solid and the liquid, you can create like this. This is this solid solution phase diagram. Right. So that's similar to the it's similar to the phase diagram for like an ideal mixing liquid phase diagram. Like they're the same thing. In other words, we have vapor, liquid, so you can shift the condensation point by putting in. So you have like alcohol and water, and you have a phase diagram like this. They mix completely in the liquid phase, they mix completely in the vapor phase, and you have this kind of coexistence region where you get vapor and liquid and coexistence. Right. So basically the same thing happens liquid vapor as happens solid liquid. Right. This is a solid solution, and this is just a solution, just a normal solution. So is that business. I kind of went over that last time. This is just showing. So we kind of got, actually, I think it was in the last homework, like to get this equation for the chemical potential in terms of the activity, right? So the question is like, how do you mathematically kind of calculate that phase diagram from the two, you're going to have two Hildebrandt parameters for the enthalpy of interaction, and you have the compositions, which could be ideal or it could, I mean, so if it's ideal, it's just x ln x sums, right? So if you have this equation to relate the chemical potential to the activity, and activities could be the composition if it's an ideal system. Then you have delta U, and delta U is you can get from the melting point. So delta U, if it's between, here we're going liquid to solid, so it's delta U of the solid liquid transition, which is basically going to equal the heat of fusion, or the free energy change of fusion, which is a heat of fusion minus T times the entropy of fusion, right? And the entropy of fusion at the melting point is a heat of fusion divided by the temperature of fusion, because delta G is 0 at that point. So you can sub out delta H over the temperature where you are over T of fusion is going to equal this delta U, and delta U is going to be this difference between the two log of activities of the component A in the solid, component A in the liquid. Right. So basically, if you equate if you say you have to have the same chemical potential in the solid and liquid, and then you're going to subtract these two log terms. If you subtract two log terms, they just become a ratio. So ln of A liquid minus log of A solid is log of A liquid divided by A of solid. So it's like log base 10 of 100 minus log 10 would be like 2 minus 1 would give you 1. So this would be 100 by 10, give you log of 10, which is 1. Base base 10 of 10 is 1. And so that kind of works. When you subtract two log activities, you end up with log of the ratio of the activities. And that equals this chemical potential difference, which is going to be this heat of fusion thing. So then you have a way, because you can look up the heat of fusion, and that's in a table. You can look, in fact, in the NIST NIST has National Institute of Standards Technologies, like the National Institute of Health for Science, kind of, except it's a lot smaller. Like National Institute of Health is a city, National Institute of Standards is a building. So it's kind of like significantly smaller. But they have a web page where they have all the heat of meltings, all the temperature of meltings, kind of everything you'd want to know about anything's there. You just kind of click in and you can get all the information you want. You can get the heat capacity, how it changes in temperature. Here, this is a weird case where small t is temperature. Usually, almost always small t is time. So for some reason they use small t here for temperature. But anyway, so if you have an expression for heat capacity with temperature, so you're running this phase diagram with some temperature. There's an equilibrium melting point for the material. So you have to integrate Cp to get that component of the free energy. So it's a little bit more complicated than just in other words, you can get it more accurate if you do include the heat capacity. You could say there's no heat capacity change when you go through the temperature, and then you just have the other equation.
Oh, gato. Hey, also me more that's life.
We could listen, but not polite. Anyway, so that's how it works. So you can get this relationship. You can define this delta U, and then you have, so the A is what you want. You want the composition of phase separation. Then you have the enthalpy value from the NIST webpage. You have the heat of fusion from this webpage. So you can include the heat capacity to make it slightly more complicated if you want to get more accurate. But then you can get this delta U. You can get the A's. So the A's will involve, basically A's is like gamma X, and gamma we can get from the Hildebrandt parameter. Like gamma A12 times X2 squared is ln of gamma 1. Right. So if you know the Hildebrandt parameter, you know the composition, you get the gamma, you know the gamma, you know the X, you can get the A. Right. So you can get everything to predict this phase diagram using that model. if you know the heat of fusion and the temperature of melting for the equilibrium, at the equilibrium melting point for the pure components that you can get from the NIST webpage. So you know everything you need to know, right? So first off, you can forget about the gammas and just say, like, I'm going to say it's ideal, so that A is X. Then I have an equation for X liquid is related to X solid. In terms of these numbers, I know the heat of fusion, the melting point, and the temperature where I'm sitting, which I know, right? Then I can get the equilibrium between those two. And I can do the same thing for the B component liquid, B component and solid. And then this delta H is the heat of fusion for the pure B, like in other words, pure germanium, pure silicon. And then you use that XA liquid plus XB liquid has to be 1. XA solid plus XB solid has to be 1. So you have 4 equations and 4 unknowns, so you can solve it. So you can solve for so you can predict at that temperature the points on this phase diagram. Right? I mean, it's just kind of a math thing. You spit out this equation, just solve, and you can get points on that. And if you can get the points on that, then you can solve the whole phase diagram. So you can do that, assuming ideal that you have no Hildebrandt mixing, right? That it's just that A is X. I mean, you have A12 is 0, right? So in that case, you get the dash for silicon and germanium. It's a pretty good guess. So the solid lines are an experimental dashed lines, which are calculating assuming solid and liquid solutions ideal, and then actually with a CP. So even with no Hildebrandt mixing parameter, these are like a perfect match. Like this is an ideal solution, ideal solid solution almost. The Hildebrandt would shift the dash up to the line, which is kind of insignificant for the system. Right? So anyway, so just the simplest possible thing. I mean, it might seem a little slightly complicated, but basically this is absolutely the simplest thing. It's just based on this stupid marble mixing and not even adding in an enthalpy term. So just marble mixing. Then you can predict this and predict the germanium silicon phase diagram, right? Which would seem impossible at first glance. Like you look at that and you say, what kind of model would I use to calculate this thing? Like it'd just be like, you'd be looking at it for a long time. You know? But basically, if you go through the routine and you start with the simple, and you just assume everything is the same as the simple, and then you go through a couple tricks, like kind of math tricks with the enthalpy, then boom, you can calculate it. So that's kind of the power of this approach, like the thermodynamic approach. That you can so you can say like, oh yeah, it's just someone's dream that you have these this entropic law, and it's just some goofy thing, and it's like some kind of thing you can study it, and maybe it works, maybe it doesn't, probably doesn't. But then you go ahead and you do silicon germanium, it's exactly right. You know, so it should be kind of shocking that you can do that, given the simplicity of the model. Right? To me, it's shocking, like that you could possibly do that with such a simple idea. Anyway, so it's that business, and then this has shown the deviation from using actual heat capacity and not letting the heat capacity change. This is for a more complex, so the situation gets worse. So this is a pretty simple thing, like diamond cubics, a pretty simple crystal structure, and the two things have almost the same size. So if you start looking at things that have polarity, like oxides, then things aren't as nice, right? So the model calculation kind of matches. You can see this, what you're looking at is like a positive deviation in other words, there's a gamma involved. That means that these oxides kind of have an attraction for each other because they're polar, right? So things are not going to be, there's no polarity in silicon germanium. They're just these spheres, essentially spheres that fit into, they're like marbles. So this should work, and this shouldn't work. So there's some slight deviation that you can account for. So the heat capacity, like adding in a heat capacity term to go from the ideal heat of fusion, whatever temperature silicon and germanium melt, to the actual temperature where you are. So this integral would be from this like 1680 to wherever you are down like 1400 to get the heat capacity change for the material. So it's that affects the free energy. But you have to add in a heat capacity term because it takes energy to go from heat of fusion of the pure component to wherever you are. And you can get that with these kind of polynomial Taylor series expressions for the heat capacity. So these are always going to be like this power series, and the integral is going to be one more power up. Right? So you end up with, and you can just put that into a computer program and it spits it out to do that integral. So you do like a step integral. So it's not hard to do that. Anyway, so that's the idea. I mean, that's kind of how this CalFAD and this other program, the MAC program, are going to work. I mean, they're going to just be plugging in parameters into these simple models and then just spitting out kind of what the phase diagram looks like. And they work, like this whole thing works, right? So what about this? This is a congruent melting. So you have, so this is just like, so we said like that would be like eutectic, right? So for, if you're doing like chemical engineering and you have liquids vapor, you try to distill it, distillation will go down these steps. And you get to this spot where you can't distill it anymore. Like it's not going to do any good to go through another stage. So it's stuck. That's as clean as you can get it, right? So to break, like you can break an azeotrope by putting another component in to shift it. There's a couple other things you can do, or you can put it through a membrane and do the separation, or do some other technique to separate, right? But so anyway, here the same thing, right? It's a congruent melting system. So again, this is like the bread and butter for chemical engineering. This is kind of a nuance for and this is the bread and butter for materials, right? The eutectic. So sorry, to get that, all you need to do is have an odd shaped equilibrium or free energy curve for the solid, right? So you have, it's flat and make the liquid a little bit steeper, and then you get, instead of one inflection, one crossing point, you have two. So basically you end up with two of these biphasic regions, and you end up with a congruent melting, where congruent means that the composition of the liquid is the same as the composition of the solid. So it melts or crystallizes at the same composition. If you're in this other phase diagram, so you're gonna drop down here, and it's gonna separate into that. It's in equilibrium with a different composition. So it's not congruent. It's incongruent, in fact, because you have a different composition of the liquid and the solid. Right. So, and that only happens at the one congruent kind of critical point, this thing. Right. And you're gonna have the two solids. So the solids are miscible here. So KCl and NaCl are miscible, completely miscible in the solid phase. But you have the KCl rich crystal here and the NaCl rich crystal here. And the liquid's completely miscible also. Right. So you don't have two different crystal forms. You have two different crystal forms, and you need another curve here. That's another phase. The same crystal form, it's a solution. It just follows that Hildebrand equation. Different crystal forms, you need two Hildebrand equations, one for each crystal phase. So anyway, so that's how this thing works. You're going to have, so you can see this there's a tangent, common tangent here for the two curves. It's kind of hard to see, but there's 2 points there that would correspond to like these 2 points. And there's also 2 points over here that have the same chemical potentials, just change in G with X, and those two are in equilibrium, and they give like those 2 points. So at the same, this is at this temperature, 105, you can have two areas of common phase, and in the middle, the liquid dominates. Any place on the liquid curve, it's going to bounce back if you have a fluctuation. And then when you get to the, well, there's no edge on this. You have, well, there would be an edge. This is that phase, this is at this temperature. So at that temperature, so you'd have to go to a temperature where you reach this point, and then those two curves would coincide to a point, just like it did in that other plot. It would be like they would collapse into a single point like that, and that would be that point where the thing meets. Right? It would be the same thing. Right. So anyway, that's how you get the next step of complication, which is congruent melting. So it's kind of like this. I mean, you could think of this, that you've separated the phase diagram into two regions like this. In other words, you have two lenticular regions, one there, one here, and it's just flipped over. In other words, the composition goes backwards on the other one. So you could think of this, at this point, you could think of that congruent melting composition as like another phase, like the magic phase almost, right? And that would be a congruent melting temperature. So that at that point, that's when the solid, in other words, the solid curve will drop, the liquid curve will rise, and there's a point where they just touch in the middle. And that's almost like a magic composition, like where everything, like all the planets align, whatever, the age of Aquarius, I guess, for the thing. That's a song from Hair, the musical from the 60s, whatever. Anyway, I was there. So anyway, so if you want the eutectic, you just amp it up one more notch, right? So you have two crystals, a liquid. So in your T1, so each of these curves again is going to be x ln x, and then maybe another term if you want to add it in. Right now it isn't added in, it's just ideal, right? So anyway, so you have and if you know the equilibrium melting point and you know the equilibrium heat of fusion for the components, and maybe if you know the heat capacity for that pure component as a function of temperature, which would help, but you don't need it, then you can calculate these compositions, right? You don't need anything else. If you say it's ideal, if it's not ideal, you need a gamma. You need one other term if it's not an ideal mixing, right? So anyway, so it's the same game. It's just like you get more equations, right? So you have an equation for that, equation for that, equation for this. If you're in the liquid state, the liquid is the lowest. At any point here, it's going to be happy because any fluctuation, it will go more uphill than downhill. They'll spring back. It's like a spring, right? So any fluctuation drives back to the original. Then you go to T2. So T2, it doesn't have, so there's two crystalline phases here in this. It's like yttria and magnesium, right? So oxides. So there's two different oxidation states, I guess. Let's see. No, they're just two different crystal forms. It's a cubic and hexagonal, I guess. Right. So the same oxidation state and everything. So basically you just have so in that case, as you drop the temperature, then you're going to have only the magnesium oxide is showing up. So still over here, the liquid is still happy land, like it's a smile face with two eyes here. And then magnesium, so there's going to be a common tangent for the two. That means you have equilibrium between that phase and that phase. That's going to be these two, this and that point. If you're to the left of it, it's a happy phase for the magnesium solid solution. It's going to have some yttria oxide in it. And if you're over here, it's a happy phase for the liquid. Right? So it's liquid, then the solid solution. Drop it a little bit forward, you get into this yttria phase. So it's a cubic yttria phase. And so by the Gibbs rule, you're going to have a two-phase region between the two single-phase regions. The Gibbs phase rule tells you that you need to have this two-phase region here. Like if you figure out the degrees of freedom, it works out that you need the two. And you notice this pure hexagonal yttria oxide, this thing just touches there. So at this T3, there's this guy, then you're going to have those two just touching right at the edge, the cubic and the hexagonal. So each of those phases has its own x1 ln x1, x2 ln x2 plus whatever the other thing is, right? So they all, so anyway, so you have 1, 2, 3, 4 curves in this thing. This is only showing cubic, but it's also hexagonal, right? So if you're at this temperature, there's a common tangent here, that gives you that and that. There's a common tangent here and there, that gives you this and that. And then there's like this point over here where the two curves collapse on each other, and that's just where these two collapse on each other here. So the two phase curves like meet at that point, right? So anyway, this plot kind of shows how that works. And then it goes to T4, which is below the eutectic. So at the eutectic, the liquid curve and the two oxide curves would all coincide at that composition. So they'd all touch each other, right? When you're below that, when you're below that, so T4, T4 doesn't have any liquid. It's just the two crystals, right, forming here. So you have, so the two crystals, so there's a common tangent between the two crystals. That's the point. So there's one here, one there. It almost touches a liquid. The liquid shouldn't be that close here, but it seems to be. Maybe, oh, I'm looking at T5. T4, sorry, T4 is the, sorry, T4 is the eutectic temperature. And the eutectic point is where those two phases meet the liquid. Right, so T4 is the eutectic. And then it's got, that's the common tangent with the liquid is a common tangent with the crystal. So you have three phases in equilibrium. And then you have to the left of it, it's kind of a smiley face you can't see for the magnesium oxide. To the right of it, it's a smiley face for the yttria. All right, so you have the single phases of those two solid solutions. And in between, you're going to separate into those two, or you could equally go into the liquid. So if you're an atom and you're an oxide in the liquid phase, you're just as happy to go over here as you are to go over here as you are to stay in the liquid. Like they're at equilibrium right at that point, at that composition at those temperatures. Right, so there's no driving force because the chemical potential for that phase, and that phase are all the same. The slope is the same. So that means that any oxide that's here is just as happy, and the liquid is just as happy there. And everything's moving around all the time, so they're constantly flipping from one phase to the other. Meaning that if you have a fine powder of the yttria oxide and the magnesium oxide and the liquid, so they're just going to meld together, get rid of the surface area, and they'll just turn into a chunk. Or else they'll just completely turn into the liquid. Like you can't tell what's going to happen. There's no predicting what happens when you're at a critical point like that. Anything can happen. Right? So it could all just turn to liquid, it could all just mold into a magnesium oxide, it could all just mold into a yttrium oxide. So it can go into anything. Then you go below and it's just the two. So there's an equilibrium between those two and the liquid's out of the picture. Right. So just by having these three Hildebrandt kind of equations, you can predict the eutectic thing. You fully predict it. Right? So that means what you need are the heat of melting for the three crystals, the melting temperature of the three crystals. So 6 parameters. And then that's it. If you assume ideally you need 6 parameters to predict this whole thing. And then you need 4 more, so you need 10 parameters to actually with the enthalpy of interaction, which you'd need for magnesium oxide, right? So you need 10 parameters. It becomes like a lot of parameters, but each parameter, right? So you can say 10 parameters to get this, but count the features that you have in the plot. Like you have that point, that point, that point. Each of the point has 2 parameters. That's 3, 4, 5, 6, 7, 8, 9, 7, 8. So you have 16 features you can go after, 16 points, and you're only using 10 to predict the whole thing. So it's with parameters, if you can, all right, so number of parameters is important. Like a lot of parameters, so if you do a power series with 10 parameters, it's going up to x to the 10 or x to the 9, then you say like, well, that could fit anything. But basically, if your parameters are constrained, right, to each of these things, and then you count like how many points you have in your data. In other words, your data is a straight line. Well, there's 2 parameters, and you fit it with a 10 parameter model, you're making up like 8 parameters that don't have any meaning, right? But if you can count how many points you have and then how many actual numbers you get from those points, and if it's significantly larger than the number of parameters, or even if it's equal to it, then it's at least possible if you could get an error bar in the values of your fit. Right, so yeah, it's 10 parameters. It's based on a simple model. Basically, the 10 parameters are giving you 14 spots in this curve. 14 numbers, 7 spots, 14 numbers. So that's a good trade-off. That's a good deal. You should say yes to that deal. You know, like if it's buying a car or something. But anyway, so if you want to include the the gamma Let's see, how do you include the gamma? It's just gonna be adding in another term for the gamma here. So you have, all right, so you have this ln x ln gamma. So, and you know that ln of gamma is omega, or A12 times, so of A is xb squared. We figured out how to get that at some point, but, or you can just accept that. Then you can substitute in for that. So ln xa times ln gamma, or ln xa gamma a is ln xa plus ln gamma a. And ln gamma a is going to be this omega xb squared. So you could just add in those terms, right? So you have 1 minus xb, so which was xa, and then gamma a is xb squared. So you just call it in terms of xb times the gamma in the liquid phase and the gamma in each of the crystal phases. Well, here it's just one crystal phase, but you could have 3 or 4 crystal phases, right? So basically you do the same balance, but you're adding in this term. It's the same thing as before with the same delta mu. That's a heat of melting, temperature of melting, heat capacity. And you just are adding in this term that you got from this thing, because you're substituting just x for x gamma to get the activity. And then you convert the ln of gamma into the x squared thing, and that becomes this term. All right, so you have two for every phase. You have one more parameter. So if you have 3 phases, it's 3 parameters you add to it. All right, so in the other one we had 3 crystals in a liquid, so we had 4. So that would get us to I guess that's how we got to the 10, maybe. So basically that's going to add, for this case, it'll add 2, like a liquid gamma and a solid and a crystal gamma. Right. But anyway, so then you can solve that the same way, because gamma, presumably you know what gamma is. If not, if you don't know what gamma is and you have the phase diagram, so you can pick, so how many points can you get out of this phase diagram? You can get like as many as you want, right? You can get like a point here, there, 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 there. You can do measurements. So you just need 2 measurements to get the gammas. Once you have the 2 measurements, then you can go back and figure out what the gamma is, and then you can predict all the rest of the phase diagram. So the advantage of this is you don't have to measure the entire phase diagram. You just need to measure 2. If you don't know, you might know those parameters. If you don't know the parameters, 2 points will give you those parameters. So you have to make 2 samples, measure the phase behavior, and you can predict the whole phase diagram. It's a good deal. So that's like a pretty good deal. It allows you to predict like kind of everything that's going on and do it in kind of a mysterious way. This is just showing better, like that. This is just a liquid phase separation. We already talked about that, I think. That's a reason to show that is because that's kind of like the main thing for polymers. I don't have any citation here, but this is kind of how you do the polymer phase behavior. I showed you the PVME, the stuff that's supposed to phase separate when you put it in your hand with water, and that mixes with polystyrene, which is like a Scotch tape container. Those 2. So there's not many polymers that mix. For some reason, these 2 mix. Like this is, I guess this has a lot of electrons, and that's kind of electronegative. So kind of the methyl group is in need of electrons. It kind of attracts to this aromatic ring. So these things mix for some reason. You can get a phase behavior from it. This is kind of a rubber, and that's a glassy. So mixing the 2 gives you something that's tough, kind of. This thing also crystallizes though, so you get both phase separation and crystallization going on, which is something that isn't. So it looks a lot like what's going on with the eutectic or something, where you have crystallization and phase separation. Anyway, the fields don't mix very well. Like polymer phase behavior and metal phase behavior, they don't use enough of each other's concepts, I think. Yeah, because something that's really foreign here, like something could crystallize, it's just like the bread and butter in metallurgy for phase behavior. And so it's easy to predict it there. And here, this is like some wrench that gets into the gears type thing. So anyway, so there is room to make some mileage out of these things. What is this? Oh, all right. So in the book, I think this is directly from the book. So this is a nice little part, and I think he invented this, or he got it from some paper, right? But so it's pretty neat. I haven't seen it before. So he has the quote unquote simple equations, right? And he has two parameters, Hildebrandt for liquid, Hildebrandt for solid. And he's going to just say, what if I take that equation? So this is ideal mixing, and this is enthalpy. And he just has the melting, and he fixes the melting temperature and enthalpy. And he just forgets about CP. And he's just going to tweak like that Hildebrandt and this Hildebrandt. So they could both be zero and they have ideal mixing. Right. So that would be just, there'd be no separation. So he says like, or let's see, ideal mix, if there's zero, then you get this solid solution that we saw, the first one. If you make the liquid negative, then you get not solid solution. This is just what do they call this? This is just solid liquid equilibrium, right? And then if you make liquid negative, which means that you stabilize the liquid. So if you have a negative, that means you're making the liquid more miscible than the solid. Then you get this congruent melting curve. So you can see like he's just demonstrating that this is a really simple game. Like you just have to play with these two numbers. So you have like basically a joystick, you do X and Y, so two numbers, and with changing X and Y, you can get every possible kind of phase behavior, which is, I mean, it's impressive, like if you look at it that way. I mean, if you made this into a video game, it would be more impressive, you know, I guess. But so anyway, when there's 0, 0, you get the ideal mixing. You also get congruent mixing if you destabilize the liquid, but it's a different kind of congruent melting. Right? It's kind of like an upper, and this is a lower. But this would be kind of an upper because you heat up. Let's see. This would be a lower, that would be an upper. I guess we look at it in terms of critical solution temperatures. So then if you start playing around with destabilize a solid, stabilize a liquid, then it's possible to get this behavior. You have a solid crystal, two solid crystals forming, right? And if you destabilize the solid and keep the liquid alone, you broaden out those. So destabilizing the solid means you get A solid and B solid separate. And then if you destabilize everything, then you get this mess. So it's possible to like, and these are just using 15. If you change the values, you can get even more complicated things. Right. So you can see like there's a lot of room for getting weird phase behavior just with the absolute simplest model for this thing. So I guess that's it for that thing. Oh, and then, all right, then you have this other thing, right? This is the solution. So, oh yeah, so just invariant points where you have a point on the phase diagram. Of those, it's like a bunch of different types. So this is in terms of nomenclature, people talk about it. Otherwise, maybe it's not that important. But basically, this is kind of one of the things from undergrad materials, I think. So you have azeotrope, congruent melting, then paratectic, eutectic. We know about eutectic. So liquid goes to two solids. Paratectic is like three solids. So you have a solid going to two solids. Monotectic is liquid to another liquid in a solid, and syntectic is two liquids going to a solid. So all those kinds of phase behaviors exist, and you can find them. If you work with one system, then you'll see that. I mean, you'll be using it, and if not, these are just words, I guess. But there are some examples in the book about the different kinds of phase behavior. So these are places where you have three phases in equilibrium, right? So then there's this issue which is important to metals and ceramics, right? That you have especially ceramics. You have like a magic composition where it's like a compound. You take two ceramic like zirconia and calcium, and then all of a sudden there's a material that's an absolute perfect match, like a certain kind of crystal form. I'm not sure what that is, but anyway, so this is some kind of, so the things just snap together, and then that thing has a really low free energy. Meaning that, and only at one point, if you vary the composition, it doesn't exist. So it goes back to zirconium oxide, or goes to calcium oxide, if you deviate at all from that. So in the phase diagram, those things are just going to be, so you can see, like, you could have a common tangent to this thing. It's a point, but so it has any common tangent. So if you draw a line to go tangent with the zirconia, and a line to go tangent with the calcium, then you have a region of equilibria between the calcium oxide and this intermediate phase. So this thing becomes like a line on a phase diagram. Like, in other words, it becomes as if you had the phase diagram and drew a line through it, and you had the two phases there. So you have these equilibria points, whatever temperature this is, between the intermediate phase and whatever the calcium salt solution over here, right? And the same on the other side, between that and that, you have some kind of equilibria between this cubic zirconia and that phase. And you can see, like, there's more than one here. So you can think of these as like, da, 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 click. That's the perfect thing. Then da, 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 click, click. It's got, there's three of them in this. Maybe, not sure if that's another one. Basically, there's many of these intermediate phases in this phase diagram that just show up. I mean, are you working at ungodly temperatures? So, but basically these things exist, right? So people have mapped these out. It's a feature in phase diagrams. It's kind of a dominant feature. Right? So this is titania, silica titania. So those are, or silicon titanium, right? So basically, there's a bunch of intermediate phases for that. So this is like sand is SiO2 mixed with TiO2. TiSi is like common if you purify it, right? So anyway, so there's quite a few intermediate phases in that system. I mean, you can see that this intermediate phase thing shows up. The monotectic liquid to liquid 2 plus alpha is kind of a weird thing, but it does exist. There, I think on the web page is a self-lubricating bearing thing that shows a monotectic. And there's another paper on bismuth. So if you go over to the web page, there's a bunch of papers there on this stuff, this phase behavior. Tactics. I think this bismuth is a monotectic. I think that's the one that's monotectic. Solder alloys. At some point, this thing has a monotectic in it, I think. But if you want, you can flip through those. Intermediates. Some of the nickel alloy things for jet engine blades and stuff. This links to CalFad for a PC, and some of those will link to the well, that doesn't link to CalFad. CalFad's linked back up here somewhere. I think. If you just Google CalFad, it's in here. If you want to play around with that. Yeah, this gets off on some kind of crazy things. So anyway, I thought this week's homework, you want to do that. Oh, let's see, there is something else in this, right? Oh yeah, the freezing point depression thing. All right, so this is kind of, so you end up this equation, right? So the freezing point, and then the freezing point of the pure substance, this is like salt and water to melt the salt. So you're going to lower the freezing point depending on how much salt you put in the Y. Times the freezing point squared divided by delta HF, which is just like the Van Hoff equation upside down, kind of. We had delta H over T squared for Van Hoff and Clausius-Clapeyron, right? So it kind of looks like that. It's kind of based on the similar approach, I guess, the chemical potential. And then if you have a pure component, the activity is 1, so log of 1, 0, so that term drops out. If you say isobaric, the VDP drops out, and you just have delta S dt. And then this shouldn't be Henry's law, this should be Raoult's law. But basically, if you say ln y and mu, that's Raoult's law, right? If it's Henry's law, that would be H. But anyway, the concentration in the solution of the salt, say salt water, and then you have S delta T, like just the original one for mu. And then, anyway, so you keep this, but you say, so exponential minus x expands to 1 minus x plus x squared over 2 minus x cubed over 3 factorial, etc. Right? So you take the first two terms of x is small and y is small here. Then it's e to the minus x is 1 minus x. It means ln of 1 minus x is minus x. So ln of y of b is ln of 1 minus y of a, 1 minus x. So you end up with minus y of a for that term. That was a concentration of the water in the thing, I guess. Should be the salt. Anyway, somehow that, oh yeah, this should be the water concentration. You end up with the salt concentration here. So then you can say, like, you can replace this ln y of b with dya, and then you have the s term, so you end up with delta s, and dya, delta s rt dt, and s is delta h over t, so you have dt over t, which will give you ln of t, and then on this side you have dya. If you integrate it, you're going to get ln of the t ratio, the prefactor is delta h over rt. And then you use the same thing if t freezing point over that. So if you're close to the freezing point, then that number is small. And then you can say expand that log term to x minus 1. Then you can get this thing to be t fp over f minus 1. And that ends up giving you delta t over t squared, because tf over tf, so t freezing point minus tf is delta t, and then it's divided by tf, so it's tf squared. So you end up with kind of the Van Hoff equation. So you want to get delta t, that's t minus t freezing point minus t infinity. So you have t freezing point minus t infinity, then negative 1 over this thing. So you get ya times that. So you end up with that equation. Anyway, so it's possible to get the freezing point depression equation. Our book doesn't do that. Our book gives like this equation for the freezing point depression, which looks a lot more. Anyway, this is kind of straightforward if you go through it on your own. I just zip through it, but basically this thing isn't that easy to figure out, like what exactly he's doing and where these parameters come from. But this is what our book gives for the same delta t. So it's kind of the same, roughly the same equation, more or less. Like it kind of looks like it at least, but that's the standard equation for freezing point depression. But I'm not sure why this is in this chapter even, but it is. Right, so if you have a dilute thing that's shifting the freezing point, use that equation to get it. Oh, and there's one other thing. So the ternary phase diagram. So if you have, I don't know if you guys have seen those before. Basically, you end up with something like you go across temperature. You have 3 components, and you can define the phases within the 3 components. And you have like pure A, pure B, pure C, and then to figure out, you can figure out the composition of A by doing tangents to the lines on this, or you can do this kind of intercept calculation that gives you the percentages too. Anyway, we aren't really dealing with those, but you might run into ternary phase diagrams. So the trick is that this is at the compositions change, but this is at a fixed temperature, fixed pressure, fixed volume. So everything that's in a normal phase diagram is fixed. And then you just look at the composition at that temperature, that pressure, that volume, or that density. And then if you want to change one of the parameters, like the temperature, then you plot the ternaries in a 3D plot. So you get phase spaces that way in this thing. And you can do slices of that to get these kind of things. And there's ways to do tie lines in this. So phases that are in equilibria. So it's a whole kind of field. If you get into ternary phase diagrams, you'll have to figure it out, I think. But this maybe I'll talk about later a little bit on predominance diagrams. All right, so I want to go to the home. Any questions on that stuff? Or that? So yeah, let's see, hide that, get rid of this. Oops. Problem here. Here. So anyway. So I thought I'd put in, I wanted to do something on batteries, you know, I found this paper. So it's in nature. So it's kind of an odd thing. So all it is like processing, how to process what looks like kind of a high entropy alloy, right? It's like a multi-component. It's cobalt, nickel, manganese, and something else in this thing. Let's see. Oops. Like that. So he says, like, let's see, what is the composition he's working with? Here, lithium. So it's a lithium ion battery. So you have lithium ions in a phosphate solution. Then there's usually graphite on the one side. I mean, in the traditional way, and the lithium ions can intercalate. So the graphite sheets of carbon, like hexagonal sheets, and lithium can park into it. Right, and so lithium ion plus an electron goes into the intercalated sheet of graphite. That's the anode usually. And then there's a phosphate salt of lithium ions, and there's a separator that keeps the two electrodes apart. And there's a cathode, which is this stuff, which is also a cage structure. It's also a sheet structure, right? But generally, if it's cobalt oxide, so the lithium ion Li plus also combines with an electron and goes into this sheet also. So both sides are like an electron adds the lithium ion, and then it kind of condenses into this sheet structure. But in this case, you get an extra electron because the cobalt goes from cobalt +3 to +4. So when the lithium goes into this structure, it releases an electron from the cobalt. And the lithium sucks up an electron to become ground state lithium inside the sheet structure, but the cobalt loses an electron. And it's 3.5 volts. So it's a lot of voltage. Normally these cells are like 1 volt or 2 volts. Like a lead acid is 2 volts. So this is a lot more voltage. And lithium's really light. The problem is that cobalt comes from DRC and is mined by little kids. Literally, they go into these holes and pull out rocks, right? So it's kind of like a nasty material. And the same with manganese. It's kind of like, so those rare earth metals are like, there's a lot of political baggage along with them. And you need the cobalt to do this operation, you know, so, but it's cheap, you know, because the kids are mining it. Basically, also, even the, you know, the DRC's been at war for like a long time, and the rebel groups, or whatever you want to call them, guys running around with guns, get the cobalt coltan from the little kids and sell it. There's like an open market to sell the rocks, you know. So it's kind of like slavery almost involved in it too. But that said, these guys got a paper in Nature. So basically the idea is you just take a mixture with this composition of the powders, right? I mean, the oxide comes on its own. They put in the lithium, manganese, nickel, and cobalt just in that combination. And then it's a powder, and then you kind of maybe mill it and then melt it, and then you make the electrode. That's the idea, right? So it's pretty, you wouldn't think that would work, but these things form, they form a, what do they form? I lost the name of that crystal. They form a special crystal anyway. That's going to have this sheet-like structure in it, which allows this whole operation to happen. What? Oh, part
D talks about the crystal.
Oh yeah. The what's the name of it? I'm thinking perovskite, but that's not it. Spinel. Yeah, it's a spinel. So normally spinel, all right. So they have M304 spinel. So 04 would be 8, right? And then B2 is a 3 plus 3. So 04 is -2, so -8. B2 is +3, so 6. an ace plus 2. Yeah, so they have M304. So the question is like how that's a spinel. Right, so anyway, this in the spinel has a sheet structure, so that's the advantage. It has kind of like holes that the lithium can fit into. Anyway, so that's one of the questions. Thanks. All right, so anyway, all they do, so they mix it together, and there's problems with it, that it doesn't form the right kind of crystals, like not large, too large or too small. So they want to control the crystal growth in this thing. And to do that, they add this salt, right? So they're mixing this in some called a plenary mixer. A Thinky mixer is a brand, but plenary mixer means it's got a cup. The cup like goes around like that, and at the same time, it's like spinning at 4,000 RPM. So you can throw anything into it and it just obliterates it. So it's designed to obliterate whatever you put in, mix it. But the cup's made of polypropylene. It melts at 166 C. Right, and if you look at the so they put in some of these salts. They can put in pure lithium nitride, right, or pure, I guess this is hydroxide, and it doesn't do anything. Like they don't get a good grinding out of this thing. And then they put in something here, it doesn't get a good grinding, but if they put in the eutectic on this thing, then all of a sudden they get a good grinding. So you think, okay, like so it's melting the eutectic at 183 or 191. There's another phase in here. There's a separate phase in this region, right? So, which is Li2OH and solid, whatever. So there's another phase in there. So it's like a dual eutectic something or other. I'm not sure what goes liquid to. I guess that, let's see. This is I see. This is an intermediate phase. So that's an exact match. At that temperature, if you heat it up, you get liquid and this lithium hydroxide. There's an intermediate in the middle here. The perfect match. And then that's an equilibrium liquid in this thing, which is, this is a solid solution. That's just like a complete mixture. And the same thing here is a solid solution. And there's a solid solution at the bottom, right, between the intermetallic and anyway, so it's a little bit slightly complicated, basically just a eutectic phase diagram with this little twist in the middle and this intermediate phase. So anyway, 183, but the cup, like the white cup here, melts at 166. So if you reach that point and you actually melted the salt, and then that did something to these complex mixture to make it so that you can grind the particles better, which they argue it's like not really possible because your cup would melt. Like that plastic cup would just be destroyed. Right. So it's kind of a quagmire they have. So they invent a thing called a local melting. They say they have a local, something happens locally and it doesn't melt the cup. Right, that's their answer to this. And because of that, that's a Nature paper. It's pretty weird. It's pretty strange, Right. It's an important topic, but basically it doesn't seem like they did much other than sticking the eutectic, which has the lowest melting point, into when they found out, oh, the eutectic works better than the other ones. So it's kind of an example of how you can get a Nature paper if you're from MIT. I guess they're from MIT. And the other guys are from, this place, I don't know. UNIST isn't the best school in Korea. I don't know that school either. So basically the MIT thing seemed to carry them through here. So it's just, I think it's just kind of a simple thing. It just gets you to look at lithium ion batteries. That's the main point of this, to kind of see how what kind of research people are doing to look at batteries. So that's the reason to give you this. Let's see. So yeah, so there's something about the manganese-based layered oxides. There's some kind of review articles here you can glance at. And then there's some companies selling whatever they show the structure of these batteries. That's the same thing. That's it. So basically it's just like take a look at lithium ion batteries. And then figure out how, this is kind of interesting. It's in that thing. I think it's kind of interesting. So you say like energy density of lithium ion batteries, you'd think that that would just be going crazy, right? But actually it plateaued in 2010, meaning how many like kilowatt hours you can store in a battery of a certain, I guess they're doing per liter here, but usually they be per weight. But so anyway, that plateaued out. So the issue is like, what is it that you need to do to make it go higher? And there's a lot of tricks people have. Like if you swap out the graphite and the anode with silicon, it can take up 10 times as much lithium. So you get up 10 times, this chart would suddenly go like 10, would jump up to 7,000 instead of 700. But the problem is that silicon, if it absorbs 10 times the lithium, it swells like 10 times. So it means like if you get a bad lithium ion, you get these swollen packets that look like they're going to blow up, which they could. Because of phosphate salt that's keeping the lithium ion in solution is burns, blows up. So anyway, so you could, there are and most of the growth here is due to putting small amounts of silicon into the graphite to boost it. So there's ideas about making like nanoscale silicon, because if you get below the critical flaw size for silicon, you can't crack it, so it won't break when you swell it that much. And also there's a kinetic issue with silicon with the rate of lithium getting into it. So if you have a lot of surface area, the rate's faster. So small nanoscale particles kind of can solve the anode part of this. But the problem is you have to have a balancing act between the anode and the cathode. They have to hold the same amount of lithium. Like you can't, if you just have like a really strong arm on your right and your left is like a lobster or whatever, it's not going to work. Because you can't, when you discharge it, it's only going to discharge as much as the cathode can handle. The lithiums have to go over to the other electrode. So anyway, so there are advances, like this stuff is talking about the cathode. You have to have advances on both sides of the separation barrier. You can't just have one side become like a super storage area. So this is kind of looking at the materials. This paper is looking at the materials on this side, like how can you boost the storage capacity of that cobalt oxide spinel structure that they use on that side. There's other batteries too that people are proposing. Basically, even within the scope of this thing, I mean, this would be plenty if you could make this 10 times more. That would solve all the energy problems of the Earth. You know, I mean, basically, you wouldn't need another technology. There are other technologies, but basically, that would be enough to kind of kick us over the edge. But we're already there. Actually, we're doing fine right now. The lithium ion is plenty for what we normally do. So, but 10 times better would mean that, like, you charge your car once every six, like an oil change. That's how often you'd fuel your car, for instance. I mean, you'd fuel your car once every 6 months, maybe a year, if you had 10 times the storage capacity. Right? So I mean, it could be a different world if you did that, but even the world we exist in, it's lithium ion's fine. So yeah, so that's kind of what this thing is. 4 here should be 2. So there's a phase diagram for the salts that I showed you already. It's got a little nuance in it, like there's an intermediate phase in it. It's got a eutectic and then kind of something he's kind of in the, anyway, he's looking for a low melting point, I think is the only reason he's looking here. Which is, it's kind of weird because, you know, in a eutectic, you don't usually, that's not necessarily, this is why you'd go to an azeotrope in liquids. Try to find the lowest boiling point that you could find for the solution. I mean, so using the lowest melting point, it's almost like the azeotrope trick in liquids being applied to metals or ceramics here. But it's kind of interesting they're doing that. If you slowly cool So then what happens when you go through the routine here of like looking at what maps out? It's really cool, 0.5 mole fraction, 300 to 175. So if you do that, so you're in the liquid state, and you go to 175, kind of right here, and you're at 50%. So like a lot of things happen. So there's this, you go through this, if you're going slowly, so you're coming down and you get this point.
That's at 0.45.
Oh, 0.5. Okay. Yeah, 0.45, a lot of things would happen. All right, at 0.5, so 0.5 at 300, then you're going to cool down. And then here, it's going to form, so it's going to be in equilibrium with the pure, I guess it's a pure salt here, pure LiOH, which is just like a single spot there. So it forms that phase. And then as you cool, so if you just do a slow cooling, you just get LiOH, but it's still got a small amount of, as you go deeper, you get this small amount of liquid that once you got to here would precipitate out into, so the LiOH is kind of locked in. Like that initial, if you're going slowly, you lock that in. If you kind of subcool a little bit, then you have some liquid left. That once you reach this kind of eutectic line, would form more LiOH, and then some of this. I think at some point you're going to get some of this intermetallic forming. Anyway, it's kind of complicated what would happen if you do a slow cool of that. You can say, just say it's complicated and say something about it, but and then what about a rapid quench to 100, right? So if you do a rapid quench to 100, this is the kind of game that you're looking at, right? So 300, and then you're going to quench down here to 100. Then I think that it looks like the intermediate disappears the way I see it. Is that what you see? That the intermediate disappears and you would just get, it would separate into the nitrate and the hydroxide. It would, if you did a rapid quench, it would just be those two, I think. The intermediate, I think, disappears at that point. So it only exists kind of in that region. You could quench from there down and you'd have the intermediate. But if you quenched it in here, you're just going to get the two salts, I think. You might have a different answer. Is that all right? Or
Would you not need a TDT diagram to make sure that like nothing else would form? Just go off that phase diagram.
we're just going off the phase diagram. Really, you'd need more stuff. But basically, at 0.5, and it's hard to tell what the matrix phase would be at 0.5, so you'd get some kind of weird, I mean, you wouldn't get like domains of nitrate in the hydroxide. You'd get some kind of weird mixture. Like it's hard to tell. It's hard to tell what it would be, actually. This is just the salt. So yeah, I'm not sure. Anyway, you just have to figure out what you want to say. You have to draw kind of a cartoon of what the structure would look like. So it wouldn't be like a spinodal thing. It's kind of hard to tell what it would form at 50% because you don't really have a matrix, right? You don't have a precipitate in it. So if you want to say more about it, you can, like whatever. It's good. Cooled salts that have 4 or 5 mole fraction LiOH. So that is at the green dot, right? So 250 to 187, rapid cool at 187 is, this is 150, 187 is just, so 191 and 183. So 187 is within that little skivvet thing here, which is the inner interphase and the liquid. So if you just go to there, you're between that being in equilibrium with liquid. Liquid's a smaller one, so you would have mostly this as a matrix, and you have little liquid droplets in it. See, it's between the two. Can't blow up anymore, I don't think. So basically, between the top and the bottom here. Because that's 183 and this is 191, you're at 187. So you'd form, and then if you did an equilibrium line, the liquid part, well, it's mostly liquid. So it would be liquid with little precipitates of this intermetallic forming. Yeah, it's mostly liquid, sorry. So yeah, it would be just precipitates forming in the liquid phase. So you get a powder coming out of that composition. So anyway, you can think about these and kind of argue whatever. What about a rapid quench from 250 to 175? So it's asking every possible question here. 250 to 150, 175 is like right there. So you're just going to be in the middle of this, between the intermetallic phase and the lithium nitrate. So you'd have it, and that one would be a small amount of the nitrate. So domains of the nitrate in this intermetallic matrix. And maybe spheres of this stuff and that thing. And it's going to be about 10, like maybe 5 to 10% of the spheres. Right.
Just say that again, sorry.
So you got, if you go here and you stop right there, right? Then you got to form this thing and that thing. So you have the nitrate. There's only going to be like maybe 5 to 10% nitrate. And it's going to be 95% of this intermetallic thing, that phase. So this is going to be the matrix, and going to be little domains of the nitrate in it. I mean, you might have a different answer. Some of you guys, I mean, I didn't do metallurgy undergrad exactly. I taught some of it, but they're fraction classes. But I think I taught mechanics once. So you might know more about phase diagrams than I do. And then a rapid quench from 250 to 100C. So if you go down to 100, then you just have the two salts. You just have, and if you're at 45%, that's going to be mostly the hydroxide, and it's going to be a large amount of domains of the nitrate. Right? You'll have like a bunch of domains of nitrate that are pretty big in a matrix of the hydroxide. I think for that. Then is that it? 250, and then sketch the structure. You have to make a cartoon of that. Is this another one? If you slowly cooled to 100, what structure would happen? So this is where things can get, so it's 45%. So you're slowly cooling, then you get the precipitate forming in the liquid, and the liquid phase itself, which has a composition of that. So see, when you phase separate that thing, and you have mostly liquid, so that'll precipitate out at the bottom. Then you have liquid, and it's going to have this composition. So you don't have the 45 anymore. You have that composition. Then that's going to drop down here, and you're slowly cooling. So at this point, you're going to separate into 10% of the nitrate and mostly this intermetallic phase. And as you continue to cool, then you get into this where the intermetallic wants to disintegrate into those two.
Why do we move away from 0.45?
Because when you drop slowly at 0.45, you form two phases, this precipitate, and that's draining out the hydroxide from the thing. So you shift over towards the nitrate. The composition of the liquid changes. You've depleted it, because when you make this composition, that isn't the same composition as the 45. So you've depleted it of the hydroxide. Right? So you have to have another composition. Once you pull out the hydroxide, your liquid isn't the same composition. So once you could say that you could say as you go down, you're just perceiving more of this intermetallic thing, and then you finally get to the eutectic. And now maybe you end up with the eutectic liquid. Right? And then you slowly cool that, and that's going to form the intermetallic and this nitrate, mostly the intermetallic. And if you cool further, the intermetallic might decompose into the two salts. So you're going to have one phase, the powder, two phase, this thing, and then third phase will be like, so you have 4 phases in the end. But you could potentially have 4 different kind of structures in the end, because they're formed at different kinetics, right? So Or is it, even though you have lithium nitrate, these might be bigger than those. I mean, they might be of different size. But so if you draw a cartoon of it, like they're the same composition, but they're going to be of different size because they formed under different conditions. I don't know which one's bigger, but basically these would be smaller, I think, because kinetics are a lot slower here. Or you might have, you know, kinetic, well, that's 100 C. So the kinetics are really slow. So you might not even form those two, but you could, whatever you want to say is fine. But if you did say you formed the two, that would be good. They're like, you can get all these different phases showing up. So if you look at a micrograph of that thing, no, it wouldn't be any clear answer in a micrograph. You'd have all these different domains in it of different composition. If you did SEM and got the EDAX on it, you'd find out all these different compositions and like where did they come from, you know? So yeah, so he's got some kind of kinetic process. So you just have to read what he said. I think you just read what he said and parrot whatever he said about it, I guess. Or if you disagree with it, that would be even better. But then you'd have to have some other explanation for why the green dots. In other words, he couldn't have gone above 166, right? So he's got this liquid because the cup would have melted if he'd gone above 166, and then he never could even get to the liquid phase. Like he wouldn't be possible for him to get to the liquid phase. So it's like, how did he get the stuff to melt? And then, so maybe there's a way in this phase diagram that you can get it at 166 to make a liquid salt. I don't exactly see where that is here. So, I mean,
About the mechanical agitation.
right, which sounds to me like, I don't believe it. Prove that to me, you know? Or you could Google that and see if anyone else has used that kind of excuse. Or you could just say like, this is completely made up. Like he just happened to not know the temperature or something weird happened. Maybe it was humid that day. Oh, he mentions humidity. Like the salt's going to attract water, right? And he's doing it in the room, I think. So you could say something like it was a humid day. The whole phase diagram shifts if you put water into it.
Yeah, it
Right.
says LiNO3 is sensitive to moisture. Water may also contribute to the melting and deagglomeration.
Yeah, which would mean like his whole,
Which in effect shifts the solid liquid.
which means how are you going to implement that in a battery manufacturing plant, you know, which is the main point of this thing. Because the thing has no science in it at all, right? I mean, to me, there's no science in this at all. It's in nature. It should be all science. It's just a battery manufacturing plant, like how to tweak it, right? And if it comes down to the room humidity, like it isn't even a bad science paper, right? It's just like completely. So you could rip this apart if you want. I mean, it's probably a good example of how you could take a nature, which is supposed to be the best of the best, you know, like say these people are just, you know, it's just like they throw some stuff into a cup and then they made a paper about it. I mean, in a sense, that's kind of what's going on here. In another sense, like it could change the world, I guess. So I mean, might be the super battery comes out of this, but anyway, I think it's interesting. It's good to kind of look at lithium-ion batteries because I think there's a lot of research going on in it. None at UC, but basically everywhere else. I tried to recruit like battery people, and we ended up with the two polymer guys. So that's kind of the way the world goes. You know, we had some really good battery people, and like we got polymer. And polymer's good. I like polymer. I'm a polymer person, but you know, I think this is probably